Think back for just a minute to your experience learning the new integration techniques at the first half of this class. At first, it may have seemed overwhelming, but as you started to learn the different categories and you were able to identify patterns in integrands, your confidence grew. The same thing will happen with series. At this point, you are already familiar with some specific series and some tests. We began with the user-friendly geometric series. Remember, the benefit of the geometric series is not only can we quickly tell if it converges or diverges, but we can also sum the series with a very simple formula. We also looked at telescoping series, and we looked at calculating the sum using the limit of a sequence of partial sums. Then we examined the divergence test. Here we were looking to see if the series diverged. We weren't necessarily looking at summing the series. We've also examined two comparison tests. We learned the direct comparison test and the limit comparison test. So we're going to add two more convenient tests for inconvenient series. The ratio and root tests will make a difficult series with challenging terms easy to determine convergence or divergence. So let's get started with the ratio test. Here's the theorem. Let the series a sub k be an infinite series with positive terms, and let the limit as k goes to infinity of a sub k plus 1 divided by a sub k equal rho. This is the lowercase Greek letter rho. In the ratio test, we're going to form the ratio of two successive terms. So think about the terms in a series. You have a1 plus a sub 2 plus a sub 3. We continue this pattern. We could say the general term is a sub k. The very next term is going to have a subscript that's exactly one more than the previous one. So this ratio that we're forming is the ratio of two successive terms, the later term for the numerator, the previous term for the denominator. We make our conclusion about convergence based on the value of this limit, which we're calling rho. Number 1, if 0 is less than or equal to rho less than 1, the series converges. If rho is greater than 1, including rho equal to infinity, the series diverges. Be absolutely sure that you distinguish rho from p in the p series, which, by the way, we need to add to our list up here. But rho is actually similar to the r in the geometric series. If we think about the geometric series, whose general term looks something like this, it converges for r less than 1, and it diverges for r greater than 1. So we can see a similar set of conditions on the rho for the ratio test. Associating these two sets of conditions together is a smart idea because you can, again, enhance your learning by associating it with what you already know. But this Greek letter rho is the Greek form of r. These two are chosen intentionally. As we work our way later down the infinite series and we find the ratio of successive terms, we're treating it as if it is a geometric series. If this ratio leads to the limit of rho, and rho has these specific conditions, then essentially it's resembling the geometric series over a long period of time. One more condition, number 3, if rho equals 1, the test is inconclusive. If the test is inconclusive, we've got other options to try. Now, you will find that the ratio test is useful for series which contain terms like k factorial, k to the k, some exponential terms, or even combinations thereof. Those terms are very difficult to deal with in situations such as the divergence test, specifically direct comparison, even sometimes limit comparison. But the ratio test will actually simplify those difficult terms. Let's try example 1. Determine if the following series converge or diverge, and we're going to use the ratio test. So we have the sum from n equals 1 to infinity of the quantity 2n factorial divided by n factorial squared. When we apply the ratio test, we're going to find the limit as n goes to infinity of the n plus first term divided by the nth term. That's our plan. So to find the n plus first general term, we're going to plug n plus 1, n for n, in our explicit formula here, but we have to be very careful with the parentheses and the factorials. So we're going to replace n with n plus 1. This would be incorrect because I'm just adding 1 to the parenthetical element. I want to completely replace n with n plus 1, which means I need a set of parentheses around it. Also, I want to be very careful to keep the factorial outside the grouping symbols. Quick little note, if you're not familiar with factorials, a constant times n under a factorial is not equal to the constant factorial n factorial. So be careful that you don't be tempted to distribute a factorial to the factors inside parentheses. So that means I cannot distribute this factorial here. So watch for that temptation. Still working on our n plus first term, we're going to plug n plus 1 in for this n here. So we have n plus 1 factorial, and then we're going to square that term. So there's the n plus first term in the numerator, and now in the denominator we need the nth term. And this is simply the given explicit formula, 2n factorial divided by n factorial squared. I'm going to move my limit operator down here to the left so you can identify our main fraction bar here. Okay, let's simplify. We're going to do two things. We're going to work on the distributive property in the factorials, and since we're dividing by a fraction, we're going to rewrite it as multiplying by the reciprocal of the denominator. So this is going to look like the limit as n approaches infinity. So inside here, I'm going to go ahead and distribute the 2. We have 2n plus 2 quantity factorial divided by n plus 1 factorial squared times the reciprocal of this denominator, n factorial squared over the quantity 2n factorial. Now to simplify, we're going to expand the factorials in the numerator just far enough so that we can see a common factor with the denominator. Here's what I mean. 2n plus 2 factorial. Now, just a quick review, if you're a little unfamiliar with factorial, factorial works something like this. 5 factorial, for example, is the product of 5 and all of the positive integers less than itself all the way down to 1. So if I want to expand 2n plus 2 factorial, I'm going to start with 2n plus 2 times the next integer down, that is, I'm just subtracting 1 from that term. If I subtract 1 from that factor, I end up at 2n, and that's as far as I'm going to expand, because I notice it matches this term in the denominator. For example, we could write 5 factorial as 5 times 4 times 3 factorial if we wanted to. Now I'm going to combine all of the terms in my numerator here together. So notice we have an n factorial squared. I'm going to write it as n factorial times n factorial. Now don't worry, it's going to get better on the next step. Let's work on the denominator a little bit. We have n plus 1 factorial squared. I'm going to consider one of those n plus 1 factorials. I'm going to expand it as far as n plus 1 times the next integer down, which will be n factorial, and I'm going to stop there because I notice I have an n factorial that will be able to reduce with the numerator. Then, remember we have 2 of those, so I'm going to need another n plus 1 times n factorial squared, and then we have 2n quantity factorial. Let's reduce our common factors. We've got n factorial times n factorial in the numerator. Both of those will cancel here. We have a 2n factorial, which cancels. And notice what's left. We simply have a polynomial. For ease of calculating the limit, I'm going to go ahead and FOIL everything in the numerator. We'd get 4n squared plus 2 plus 4, so plus 6n plus 2. And in the denominator, n squared plus 2n plus 1. Notice we have a rational function composed of polynomials of equal degree on the top and the bottom, so we can form the ratio of leading coefficients to obtain the limit. Remember, that only works when your numerator and denominator are of equal degree. Otherwise, you can simply apply L'Hopital's rule a couple of times over. You'll end up with the same limit. So our limit is equal to 4. So this is our rho value for the ratio test. Notice that this is greater than 1. So we can go ahead and make our conclusion. We can say, since rho is greater than 1, the series diverges by the ratio test. So what appeared to be complex at first with the factorials actually simplifies nicely using algebra under the ratio test. Let's try example B. Again, we're going to apply the ratio test. So we have the limit as n goes to infinity. We need a sub n plus 1 divided by a sub n. So we'll set this up as the limit as n goes to infinity. Finding our n plus first term simply consists of replacing all of the n's with n plus 1's. Be careful here with this one. We want to put the n plus 1 in parentheses. Now, we know that we're going to divide by a sub n, and apparently we'll be dividing by a fraction. To skip a step here, we could say, well, when we divide by a fraction, that's equivalent to multiplying by the reciprocal. So you'll get really used to this. It happens almost all the time on the ratio test. So I'm dividing by a sub n, which once again is equivalent to multiplying by its reciprocal. So when we multiply our fractions together and clean it up a little bit, we have n plus 1 to the 2/3. I'm going to write it as multiplied by the factor 2n plus 1 divided by, now when we simplify here, we can distribute the 2 to get 2n plus 2, and adding 1 to that gives us 2n plus 3 times n to the 2/3. Now, technically, we do not have a polynomial in the top or the bottom. Polynomials never have rational exponents. But we can treat this as if it is a polynomial and observe the degree of the top and the degree of the bottom. In the denominator, if I were to distribute this into the 2/3, I'd be able to easily break up those parentheses. However, notice in the numerator, I'm not going to be able to FOIL because I have this exponent in the way. So I can't multiply out the numerator. However, we could anticipate that if we were to multiply it out, the highest powered term in n plus 1 to the 2/3 would of course be n to the 2/3. If I multiply that, ignoring all the other terms, by the highest powered term in this one, we'd have n to the 2/3 times 2n to the first, which would give me 2n to the 5/3. Again, I'm not multiplying that out because that's algebraically illegal. I'm anticipating if we were able to do that, what would the degree of the highest powered term be? And we would see that it would be of degree 5/3. Observe that in the denominator, we would obtain the same leading term. We'd have 2n to the 5/3. So as n approaches infinity, the numerator is going to tend toward this term, the highest power term, and the denominator is going to tend toward that exact same thing. So essentially, we're dealing with something that follows the same nature as polynomials of equal degree. So the ratio of leading coefficients is the limit. Now, after having said all of that, our limit is 1. If you come back up here to the 3 results of our theorem, we're dealing with number 3. Rho is equal to 1, therefore the test is inconclusive. So in this particular case, the best we can do is simply say the ratio test is inconclusive since rho is equal to 1. Now, I don't know about you, but I don't like that. We still don't know what the answer is. So let's think about it. With all of the tools that we have at this point, Which test could we apply to this one to establish convergence or divergence? It's definitely not geometric, it's not telescoping, it's not a p-series. If we did the divergence test, we would find the limit is 0, so the divergence test would be inconclusive. So this whittles it down to our comparison test, direct comparison or limit comparison. Notice that if we compared it to the series, sum from n equals 1 to infinity, of the ratio of the two highest powered terms, it would be similar to a p-series. 1 over 2n to the 1/3. This is a p-series with a power less than 1, so this is a divergent p-series. Let's opt for the limit comparison test. Remember, we find the limit as n goes to infinity of the series in question, n to the 2/3, divided by 2n plus 1, divided by the series we're comparing it to, 1 over 2n to the 1/3. Let's invert and multiply like we've been doing. Probably could have done that on step 1. When we multiply the two factors in the numerator, we're going to end up with 2n, and in the denominator we have 2n plus 1. Now, because our numerator and denominator are of equal degree, the limit is the ratio of coefficients, so the limit here is 1. Now, don't forget what we're looking for in the limit comparison test. This limit is positive and finite. That's the criteria that allows me to conclude that the series in question has the same behavior as the series that we're comparing it to. So to tie up our loose ends here, we can say the series diverges by limit comparison test, LCT, limit comparison test, with a divergent p-series. And that's really how it works. Try one test. If it's inconclusive or inconvenient, try another test. Let's get back to the ratio test. Example C is another series where we have a combination of just a linear factor and an exponential function. When you have a lot of different mixed up type of functions, the ratio test is really convenient. So let's find the limit as n goes to infinity. Now we're going to find the n plus first term. So we're going to have n plus 1 times 10/9 to the n plus first power divided by the nth term. That's n times 10/9 to the nth power. When we simplify this, notice we're dividing like bases, so we can combine those exponential terms. If we have 10/9 to the n plus 1 with the same base down here, we're going to subtract the exponents. This numerator exponent n plus 1 minus n leaves behind 10/9 to the first power, just a constant. And don't forget about the n in the denominator. So ultimately here, we could take that coefficient, 10/9, in front of our limit operator, and then notice we have the limit of a rational function. The degree of the top is equal to the degree of the bottom, so the limit is the ratio of leading coefficients, which happens to be 1. So our resulting limit here is 10/9. Now remember what we're looking for. This is our rho value. Rho equal to 10/9 is bigger than 1. Like the geometric series, if rho is bigger than 1, then our series is going to diverge. So in conclusion, we could say, again, since rho is bigger than 1, the series diverges by the ratio test. Now, really be focused on which test you're working with, because notice here we're comparing rho to 1. Is it bigger than 1 or less than 1? Down here, when we're talking about our limit comparison test, what did we want to know about the limit? not how it compares to 1. We were simply looking to see, is it positive and finite? So each test will have a different set of conditions. They're easy to get mixed up. Just remember which test you're in and specifically what criteria you're looking for. Okay, the more you have experience with these complicated series, the better. So let's try example D. Notice you have an exponential, constant base, variable exponent, times a factorial, and then the problem child of a variable base and a variable exponent in the bottom. So because we have so many different types of complicated factors here, the ratio test is perfectly suited for this problem. So let's get started. We need to find the limit as n goes to infinity of the n plus first term. That's going to be 3 to the n plus 1 times n plus 1 factorial divided by, now look at this term, n plus 1 raised to the n plus 1 exponent. We're going to divide that by the nth term, or we could say multiply by the reciprocal of the nth term. So we have n to the nth power divided by 3 to the nth power times n factorial. The terms that began as difficult, stubborn terms you're going to see are going to simplify nicely with some algebra. So let's look at our 3 to the n plus first power divided by 3 to the nth power. When we're dividing like bases, we subtract the exponents, right? N plus 1 minus n gives us 1. There were more in the top than the bottom, so the leftovers remain in the top. So we have a 3 when we cancel those two terms. A similar thing happens with n to the nth power divided by n plus 1 to the n plus 1 power. Well, not exactly the same, but it's going to work out nicely. So I'm going to write that as n to the nth power. But in the denominator, I'm going to split it up as n plus 1 to the nth power times n plus 1 to the first power. Notice if we add the exponents on these like bases, we would end up with this term. Now, I didn't forget about the factorials. We still have an n plus 1 factorial in the top and an n factorial in the bottom. We can go ahead and expand that factorial in the numerator just far enough so that it cancels with the n factorial in the bottom. Now, that's very convenient because the n plus 1 from that factorial term now cancels with the n plus 1 here. Also, we can see that these two n factorials cancel as well. What we're left with is the limit as n goes to infinity. Notice we have a constant here. Let's move that in front of our limit operator so that we get it out of the way. And then n to the nth power, n plus 1 to the nth power. Since both of those factors are raised to the nth power, let's put it as a fraction raised to the nth power. Now our problem is simply to evaluate this limit. However, we have an indeterminate form. This is, in fact, an exponential indeterminate form. The base, as n goes to infinity, goes to 1, and the exponent goes to infinity. Remember, when we have an exponential indeterminate form, we need to have another side to the equation so that we can introduce logarithm. So let's suppose that 3 times the limit as n goes to infinity of n over n plus 1 to the nth power equals rho. That'll be convenient. Then we can take the natural log of both sides. Well, I think I got myself into a little bit of a mess here. I need to backtrack one step. I'm not going to be able to interchange the function and the limit with this 3 in the way. So I'm going to backtrack up here. I'm going to divide both sides by 3, so it's going to cancel here, and it'll give our rho a 1/3 coefficient. And that way we won't have the 3 right here in the way. Once that 3 is gone, now we can go ahead and switch our limit operator and our natural log function. Remember, that's necessary so that I can separate the exponent on the argument of the log, I'm going to call that rho over 3, from its argument. So let's go ahead and move this down as the coefficient on the next step. Now, examining our form here as n goes to infinity, we've got the pattern infinity times. Now, notice the argument of this logarithm is approaching 1 as n goes to infinity, and natural log of 1 is 0. So we have an indeterminate form that we need to adjust. Now, I know you know what to do. We've seen this a bunch. Remember how hard that was at first and now how second nature it is? After some practice, we're going to invert that factor and move it to the denominator. Recall the point of doing that is to obtain the correct indeterminate form, which in this case is 0 over 0. Then it is Mr. L'Hopital to the rescue, right? I think I'll sneak over here and borrow some space. We're going to individually differentiate the numerator and the denominator. Okay, so differentiating the numerator, we're going to take the n plus 1, n over n plus 1, the argument, and put that in the denominator. And we're going to multiply by the derivative of that argument in the numerator. And guess what? That's going to require the quotient rule. So finishing up our quotient rule here, that's the derivative of the numerator. Now we'll find the derivative of the denominator. Thank goodness, that one is easy, -1 over n squared. And don't forget, on the right side of my equation here, I have natural log of rho over 3. Now, what we have is a really complex fraction. So let's look at this numerator divided by this fraction. I'm going to start with that. Simplifying that fraction in the top, n plus 1 minus n leaves a 1 in the numerator, and it has an n plus 1 squared in the denominator. Now, we're dividing by a fraction, which is the same thing as multiplying by the reciprocal. Then, we're also in the main fraction area dividing by another fraction, which also can be re-expressed as multiplying by the reciprocal. I still have a natural log of rho over 3 on the right side there, I just don't have the room to write it. So when we simplify, we can cancel one of those n plus 1s, we can cancel one of these n's, and we have the limit as n goes to infinity of -n over n plus 1 equals natural log of rho over 3. So the limit is the ratio of leading coefficients with equal degrees, and we have now the value of that limit. But we need rho. So solving for rho, we have e to the -1 equals rho over 3. Rho equals 3e to the -1. Or if you prefer, 3 over e equals rho. Now, you can type that into your calculator if you like to see its size relative to 1, or you can just think about it. We know that e is about 2.7, so we have a number in the top that is bigger than the number in the bottom, so we know this number is bigger than 1. So that leads us to our conclusion. We can say, since rho is greater than 1, the series diverges by the ratio test. It was a tough series, but the ratio test knocks it out, no problem at all. Now, just looking back over the skills that are required to complete a problem like that, first of all, you got to know the ratio test and how to set it up, how to expand those factorials and cancel. Then you have to know how do you deal with a limit that has a variable base and a variable exponent. So you're introducing your logarithms, then you're manipulating it so that you get a form where you can apply L'Hopital's rule. Then you got to know how do you differentiate a natural log. Then you got to do the quotient rule, some massive algebra. You have to be able to solve a logarithmic equation. And finally, based on the value of rho, apply the analysis of the ratio test and make your conclusion. So that is an excellent problem. That's a great place to stop, don't you think?